this second part of the talk is going to be essentially symplectic topology. I'm aiming at proving 3 theorems. The first one is that the Russell cubic is flexible. The second one is to describe the XAB manifolds that I wrote before, and if there's time, the application to mirror symmetry. So for now, you can just forget everything in the first talk, except that I'm going to use it. But you know, why things are true or kind of what the pictures mean, okay, let's not talk about that for a second. So let me now talk, at least at the very beginning, about Lefschetz vibrations, what they mean, a way of thinking about them, and so on and so forth. So here's the bird's eye of our nice smooth topology world. So consider a smooth manifold M. So now, a century ago, essentially, Morse told us that you can pick a function which is generic enough, and that's going to explain how to obtain M by attaching handles, smooth handles, along, say, a ball. And the information given by this Morse function is essentially a bunch of attaching spheres. So we have an attaching link, different dimensions, and then some framings. And the 4-dimensional case of these, it's what goes by the name of Kirby calculus, and the higher dimensional thing, well, it's not very explored. So now, the right generalization of topology, in a sense, to higher dimensions is not topology, because it kind of becomes very algebraic. But as Jacek has been kind of trying to claim for years, you want to say that the Weinstein manifolds are the right generalization to topology in higher dimensions. So what you now consider here is a Weinstein manifold. So that's going to be Weinstein. So recall that this is just an open manifold, which is Liouville, and it has this superharmonic function, which makes us, you know, it allows us to say that W is obtained by attaching some Weinstein handles on it. So how do you get that? Well, theoretically, what you can do is you can pick a Morse function. Well, you already have the Morse function. But that Morse function doesn't quite encode the symplectic topology. Doesn't quite encode the legendarian along which you attach. So the complex version of a Morse function is what goes by the name of a Lefschetz vibration. And what you can think of is that you endow this W Weinstein with a Lefschetz vibration. So if you think of these as just being a map with generic complex singularities, which is just Z squared, okay? Just generalization of the double branch copper. And now, out of this, what I want to teach you is, well, which we have done in a sense, it's how to get a legendarian handle body, a Weinstein handle body for this W. So this means that I'll give you a link, which is going to be a legendarian, hence I can describe it in the front, and I don't need to specify the framing, because it's going to be a -1, because that's the only way to attach in a way that the Weinstein structure extends. And that link is going to completely represent the Weinstein structure up to Weinstein equivalence. So that's deformation of each of the things. The Liouville structure, the plurisuperharmonic function, and well, the isotopy type of W. So, okay, I should write a name here. The fact that you can always choose a Weinstein vibration over C or the disk, it's due to Emmanuel Giroux and John Parton. But what they use, which are asymptotical allomorphic techniques, is a highly non-explicit thing. So what I suggest is that instead of thinking of any Weinstein manifolds, from now on in the talk, we restrict to Stein manifolds, and even more affine. So just think of polynomial equations in Cn. And those are very nice examples that already contain a lot of symplectic topology and are subsets of these. So say affine hypersurfaces, for instance. And then how do you construct a Lefschetz vibration for them? Well, they're going to be affine hypersurfaces in some Cn, which is going to have some coordinate x1, xn. And what you can do is exactly what you do in here. In here, what you told your students is that, well, pick a generic projection onto some line, which is to say, pick a height function. Whatever, you embed M inside your big space, like in Milner's book, and then pick projection. So in here, you have already the affine thing embedded, and pick a projection here just means pick some linear thing that has x1, xn. So if I give you some polynomial equation, you can just write a Lefschetz vibration by saying, you know, x1 plus 3x2, so on. If you use all the coordinates and they are all linear, that's going to be a Lefschetz vibration. Okay? If you drop some of them, not necessarily, but it might still happen. So you're able to do this quite explicitly. And then the point is that you need to understand the vanishing cycles. So in here we had the attaching spheres, and in here what corresponds is the vanishing cycles. So let me just draw what this pi is. So in here you have some critical points. And what you do is you take a regular level set. In here it would be a genuine regular level set, like dimension 1. And here it's complex. So inside this fiber, so this fiber might be something like this. Okay. When you now approach, you start deforming this fiber towards one of the critical points, the kind of singularity that appears is exactly that one of these spheres pinches. Okay. And then the monodromy along this thing is exactly a then twist. Okay, as I explained before, as it has appeared in John's talk. So the information of pi allows you to say that W is just the fiber of pi, let me call it sigma pi, and a bunch of vanishing cycles. So vanishing cycles are exactly these spheres that contract when you approach each of the points in here. And they don't have to be the same. It might happen that I'm having this for that one, but then if I approach this other point, the one that contracts is this one, for instance. So we will have a notation for that later on. So these are the vanishing cycles. So vanishing cycles. And what's important about that is that, well, on the one hand, you have reduced dimension. You've gone from something which has dimension 2n plus 2 to something which has dimension 2n. But now you have the information of a bunch of vanishing cycles, which are exact Lagrangian spheres in there. That should be completely analogous to the contact case, reducing to some page and some monodromy given then twist, because then twist is giving exact Lagrangians. So that's exactly what's happening on the boundary of this picture. So these guys in here are as well exact Lagrangians. Exact Lagrangians in the fiber. Since they are exact Lagrangians in the fiber, and this is a Weinstein manifold, you can consider the boundary. As Chris explained, the boundary is a contact manifold now. And now you have an exact Lagrangian living inside of it. So this small interval in here is the contactization. So you can lift these vanishing cycles to legendarians. And that exactly gives the handle body of W in terms of the handle body of the fiber and a bunch of critical handle attachments, which are indicated by these vanishing cycles. So that's the general picture. Okay, now we're going to do this in a very explicit way and keep track of everything, the vanishing cycles and how to express them. What's the issue here? Well, one of the issues is that this transition to legendarians, well, we were able to do it when we had then twists. So the first thing is that we have to understand how to express some vanishing cycles in here in terms of then twists, okay, of a basis of the fiber. So here we get to the notion of a matching path, and it's going to be mildly confusing now because I'm going to explain something in here which is general theory, and that's correct, but then I'm going to explain what a bifibration is, and we're going to use each of the properties here in one of the blackboards. So let's for a second suppose that this vanishing cycle in here also has this guy. So these 2 points in here are the shrinking of the same red guy. Then I can consider this interval in here, and this blue interval lifts upstairs to a sphere, to an exact Lagrangian sphere in W. Okay, so this lifts to an exact Lagrangian sphere, and now please note the difference in W. Okay, so vanishing cycles were the spheres on the on the fiber that did contract when you go to a critical point. And now if you draw this thing, which is called a matching path, because it matches 2 critical points, it might happen that if they have the same vanishing cycles, then I get exact Lagrangian in the total manifold, in W. Okay? Is this picture understandable right now? It's important. It's gonna, okay. Great. So now we're going to move on to the bifiber. So how do we do that? So suppose we're given already this decomposition. So we have this W, which is expressed as some fiber for Lefschetz vibration and a set of vanishing cycles. So this is maybe thought of it as being like this, and then some vanishing cycles in here, as we did before. and that's sigma pi. Now, what you do is you pick another Lefschetz vibration for sigma pi. So sigma pi now is a Weinstein, because pi was a Weinstein-Lefschetz vibration, and rho is a Weinstein-Lefschetz vibration, again, on sigma pi, and now it maps to this guy in here. So let's see. That's going to have some bunch of critical points in here as well. So in here, we had the preimage of that was sigma pi, and now I could move on towards one of the critical points, and that was describing me an exact Lagrangian sphere here. Now, how do you describe exact Lagrangian spheres? Well, a way is to use matching paths. So now you take this rho, and you hope that the vanishing cycle associated to this critical point is some kind of vanishing cycle of matching path in here. So suppose that the vanishing cycle in here was green, so that's a vanishing cycle for pi. And what you hope is that this thing can be expressed as something like that. Okay? That's some matching path. Now, the first thing you need to understand is that if you draw a random path between two critical points, that's not a sphere. So it has to happen that the two vanishing cycles, that the 2 points have the same vanishing cycle, or that you go around enough such that you pick up monodromy, and then when you go back to near the second vanishing critical point, that's the real vanishing cycle. So in here I've just drawn something randomly, and maybe it's a matching path, maybe not. So what I'm going to do now is to explain some cases in which this works very well, and that we can use it in order to prove the theorems that I stated before. So in particular, so this green, can you repeat?
I'm just making sure that it's on the picture. The vanishing cycle for pi is something that lives in W.
That's no. It's something that lives in sigma pi.
Sigma.
The vanishing cycle is what gets contracted when you approach a critical point. So it's an exact Lagrangian.
It's in the fiber.
It's in the fiber.
So in the fiber.
So now you have an exact Lagrangian in the fiber.
Yes. And the fiber itself is the vibration of this.
And now you pick this bi-fiber, this second vibration, and
This is going to be the sphere that is the vanishing cycle is the left of this.
yes, that's the general strategy in order to understand the vanishing cycles.
You don't know in general what these represent?
No, we don't. No, but yeah, but we did know so little that even making very simple cases, it's actually progress. So okay, let me start with a really simple case, which is in the case that sigma pi is a plumbing of spheres in an AK thinking diagram configuration. So, so baby case 1. So sigma pi is an AK Milnor fiber. So this just means, this means that sigma pi, well, on the one hand, you can think of it as having this equation, AK plus 1, or a plumbing of spheres. So plumbing of these star ends in the following intersection form. Okay, K of them. Okay. Is that clear what this Weinstein manifold is? Which is the Milnor fiber of the AK singularity, and it's just obtained by linearly plumbing through this. So the things I was discussing in the previous wall was an A2. Okay? For instance, A2 in a surface, it's a punctured torus. A3, twice punctured torus. A4, once punctured genus 2. So, okay. Let's take this thing. So now you'll have some W that maps on C, and now this AK. What's the nice thing about the AK is that you can now project onto the X coordinate, and that thing is the Lefschetz vibration. So this is an affine manifold. A Lefschetz vibration generically would have something like X plus some linear combination of the Z's, right? But in this case, you can just pick X, and because this is already in Lefschetz form, that's a Lefschetz vibration. Just, okay. So the point now is that this projection is Lefschetz, so you can pick rho equals x. And now, what's the bifiber? So that was the fiber. And now the bifiber, somebody tells me. So who's the fiber of rho? Well, just put x equals some number. So it's just the smooth affine conic. So it's t star Sn minus 1. Okay? So that guy is t star Sn minus 1. But that's jackpot, because this means that the vanishing cycles are always the same. Because what are the possible exact Lagrangian sphere, well, up to Arnold in life, but if you just pick two things, this, and you can check in this case the vanishing cycles are all the same, are all the zero section. So this means that if my fiber sigma pi is AK, I can draw any path I want, and that describes me a sphere in AK. Okay? So, okay, hopefully that's clear. So now, well, the color on the screen. So imagine you had some sphere in here. That's, so this sphere, this had a vanishing cycle in green. And now this vanishing cycle is going to look whatever you want. I didn't read that one. But any path I draw in here describes me a Weinstein manifold W, because I'm just declaring that those are the matching paths. So let's get some practice with these things. So that's the upshot. Hence, one vanishing cycle. So for rho. Great. Some examples. Well, suppose that I draw the following thing. So the first example, A, is the following. Just I pick this guy, and I pick this. So what's this manifold? So this is the picture of that guy. This is telling me that sigma pi is t star Sn. And there's no sphere I'm drawing, so I'm not attaching anything to it. So the resulting W is t star Sn times C. So that manifold describes t star Sn times C. Okay? Dimensions, recall, were like this. Great. Now, this guy. Same thing in here. That means we still have an A1 fiber sigma pi. And what happens if I draw this vanishing cycle? What's this manifold? Well, it's what we had before. And now we're adding one vanishing cycle. And it's the only one vanishing cycle that might be. So this is actually a subcritical handle. And this passes once through it. So that's a canceling pair describing just Cm plus 1. So that guy is Cm plus 1. Described with a Morse function with a pair of canceling critical points. Okay, let's get funkier. What's this guy? Well, again, it's just attaching the same vanishing cycle, so attaching something on the unknot. So that's T star Sn plus 1. You'd be amazed by the number of confusions that these ends create. But yeah. And now we get to more interesting examples. So let's go to these two guys. So I could attach this thing, then this thing. What's sigma pi in here? Sigma pi in here is A2. If you're thinking in dimension 4, what's happening is that sigma pi is a puncture torus. And now I'm attaching in the puncture torus the first homology class and then the second homology class. So that's just Cn plus 1. And now I might attach this fella here. It's important that because there's an order in those guys, because this is oriented like that, I have to tell you the orientation. And so giving the order set of vanishing cycles. So let me just say that I first attach that guy, and then I attach this guy, and then I attach this guy. Okay? So can somebody tell me the smooth type of this? Yes. But so far, this Weinstein structure was the standard one. And here, at least to me, it's not that obvious. It should be. Okay? And now, final fun guy. So now attach the very same things, but now instead of the upper one, the lower one. So again, you will have 1, 2, and 3. So this is, again, well, let's just say it's this sometimes, okay? For instance, in dimension 6, it's this. In dimension 4, it's not, because this, well, TV is messed up. Great. So one of the first things that was extremely confusing and that we kept thinking it was wrong is that these two Weinstein manifolds are not the same. So one way of doing that is let's try to draw them. So let's draw those two guys. So great. So I must say that these all came from a conversation. I visited Boston before I was there, and in a dinner with Paul and Emmy, Paul said, no, this guy is clearly SH0, and this is SH not 0. Well, clearly didn't understand why. But now it will become extremely obvious why. So let's see. Let's try to draw these things. So we draw them. So the first thing you do is you draw sigma pi. So first, draw sigma pi. And sigma pi is what? So in these two last examples, recall that sigma pi was equal to A2. So let's draw A2. Well, that's the one we've been drawing all along. So just one in here and one in here. So if you want, these are the two one handles in the 4-dimensional case, which would correspond to the puncture 1 torus. Great. So let's give names to things, though. This first guy in here, maybe let's call it A, and this, let's call it B. And what happens is that I'm just saying that this is a basis for the Lefschetz vibration. So you have sigma pi equals A2, and Lefschetz vibration is this one, and I'm just creating a basis for the homology. So that's A, and that's B. Okay? That's just the basis. So if you wanted to draw A, that would be A, and that would be B, just passing ones. Great. And once you've drawn this, step 2, you draw the vanishing cycles. The vanishing cycles right now are not only described as spheres, but are matching paths, so vanishing cycles of pi, which are matching paths of rho. Okay? Great. So who are they? Well, you go here, behave well, and write each one of them. So who's 1? Well, let's draw D first. So let me do the example D. Who's 1? Well, this was A. This was B. What is 1 in terms of A and B? Now 3D topology should kick in. How could you describe this path in terms of these two paths? Well, this path is this, right? But this movement in a path, it's a half-then twist in the plane. So in the plane, it is fair to say that tau 1 is the result of doing, 1 is the result of doing tau B minus 1 on A. You agree with that? Does everybody remember what half-then twist is? Just this thing in the arc. Now, the beauty of this is that this half-then twist in the plane lifts upstairs to a genuine twist. And the reason why the half becomes a 1 is because z square is a double cover. So half thing downstairs becomes an actual then twist, essentially speaking. And now 2 and 3. So 2 is just B. And then 3 is A. So you have this manifold, and now you express each of the vanishing cycles as matching path, pick a basis, and express those matching paths in terms of that basis. And there are going to be some kind of then twist, at least in these cases. And now you apply exactly the previous talk. So you just draw them. So you draw 1, 2, and 3. So let's first draw 1. So tau b minus 1 of A was this guy. Okay, well, technically in higher dimensions with a cone. And then who's 2? Well, 2 is this guy. We'll agree. And then A. Yeah. I could attach A like that, but I could have started attaching A. So hopefully nobody will complain if I do that. Okay. It's a cyclic order, right? So I could attach A first and then 1 and 2. Okay. Otherwise, you can claim that this thing this thing in here goes before the infinity and comes back through here. Okay, great. But now, things are easy because this is a Legendre that we understand very well, and we can actually say that this manifold D is a standard T star Sn, Sn plus 1. Why? Well, because I've explained how to handle slide before, so we can do Legendarian calculus in there. So you take this Legendarian here. Now, recall that each of these are different component of a link. Okay? So now I can handle slide this along this. Now, handle sliding was the same thing as doing cusps if you're in a plus 1. So this is the same picture as this one, right? And then you can just forget about that one, and you'll get this picture in here. But again, you can handle slide in here, and you'll get the picture that looks like that. In here, and then this just cancels. So this is the same thing as this. And then that's the same thing as the flying saucer. Rademeister 1. Okay? This is slow. What you do in your head usually is you just pinch things. Like if you have two guys who go through the same guy, you just pinch them together and you create cusps. So yeah, you actually get quite fast these things. So great. That proves that D, there's that example. So that example in here. With this order, 3 to 1, is Stein diffeomorphic to T star Sn plus 1. And now let's do the other guy. So what happens if instead we do the different order, or if you want to think in a different way, we attach now the guy down, so 3, 2, 1. Now you do exactly the very same thing. You explain who is 1, who is 2, and who is 3. So 1 in this case is A. Sorry, wrong order. 1, 2, and 3. So 1 in this case is tau B of A. 2 is B, and 3 is A. So now you draw the fiber sigma pi, which is this A in here and this B in here. And you first draw A if you want. That's 3. Then you draw this guy. And now you draw B. But pinch here and pinch here. This manifold. And in dimension 3, this is something like O minus 2. But in dimension 6, that's actually T star S3, because there are no invariants of Legendarian 5-folds. So 2-folds in a contact 5-fold. So what's important maybe is that this guy, which we knew it had SH0, it's actually flexible. So whenever you see a Weinstein manifold, such that in its handle body decomposition, so in its front, it has some kind of zigzags, or the loose chart I explained before, but that manifold is completely uninteresting, or brutally interesting, depends on who you ask. But the point is that it has no symplectic invariance at all. And this method of starting doing things with the handles and then twisting allows you to, from some given equation, or for some given diagram, such as the ones in here, pop up a link. Okay? And, well, I don't know. I felt I needed this kind of. I really didn't understand Weinstein manifolds, and then I started to try to draw them, and clearly the then twists were the first thing you should try. And so you do it, and you start getting these kind of funny results. So, okay, I've explained AK diagrams. Oh, because he had written a paper. Yeah, It's like 20-ish pages. Yeah. No, it was clear after you proved it. Yeah. Great. Yeah. The way they computed SH was with wrap homology, though. So kind of it should be the same at the end. So if you're algebraically minded, what's happening here is that because we are able to do all these simplifications, like if you're a symplectic topologist and you work with the Lefschetz vibration, the wrap homology that you have to compute is that of the vanishing cycles. And that might be a messy complex, because maybe it has like 55 vanishing cycles. But maybe those vanishing cycles cancel, or they just become very nice. Or maybe these 55 vanishing cycles, like 40 of them are loose. So might as well forget about them. And then this legendarian calculus gives you a better complex from an algebraic viewpoint. So when you compute the DGA of legendarian contact homology, that DGA is going to be much better usually than the symplectic one. And so that's what I said, that the computation of wrap Fukaya categories becomes much easier, at least in some examples. Because you just write down the DGA and that's it. That's the wrap Fukaya category. Okay, I'm going to move on to Decay. Can you tell me the time more or less, like halfway? Great. Okay, so just another instance of a case that I'm going to use. So Decay case. So if the fiber that you have sigma pi is decay, now things are not as easy, because it's not true that there exists a fibration of decay which has only T star as n as a fiber. Okay, so this guy, if you want to think like that's something like, it's this kind of singularity, and then stabilize as many times as you want. But the nice things about this is that you can just have a standard model. So once you understand one Lefschetz vibration for that guy, you can just work in it. And I'm just going to give you an example of one. So what happens is that you get a Lefschetz vibration, which looks like this. Let me draw it like this, at least for D4. So point, square, triangle. So now this is the analog of these points. What's happening here is that I could just write points, because all the points had the same vanishing cycle. But now these don't have the same vanishing cycle. And I have to tell you what's the bifiber. So here, the bifiber sigma pi is A2. So what I'm saying is that D4 can be described as the Lefschetz vibration over C with the fiber A2. And hence, I can describe exact Lagrangians in D4 by studying matching path in here, taking into account that these points might not have the same vanishing cycle. So what I have to tell you is what the signs mean. So if you think of this as being a torus, like this guy in here will be point. This guy in here will be square. And then triangle will be tau of square of point. Okay? Whoops. Now, that means that if I pick this path, the vanishing cycle I get is this one, which means that this is nothing, okay? This is not a sphere. Because in here, the sphere collapses, but then the disk here lives happily. So this is a disk. So you don't want that. So recall that the key point in order to draw things as Dentwist was to pick a basis. So we now have to describe a D4 configuration in this diagram in here. Okay? So let's do that. Does anybody see it? So yeah, one obvious thing to do is to pick exactly that guy. So that's one vanishing cycle. This is another vanishing cycle. Do these two spheres intersect? Yes, and at one point. And like essentially intersect. If in here you would have picked a sphere like this, well, that's a bad example. Here, this intersection point was not the same as that one. That had a double thing, okay? But that's a genuine intersection point, like one intersection point in here. And now the other two guys that you can pick are these ones. Why? Because triangle was tau square of point. So going through here, you pick up the monodromy of the square. And this is a D4 basis, because it's created by an A3 basis and then one guy that touches the guy in the middle. So great. So now if you have any manifold that you can describe with a sigma pi equals decay. Then you find its vanishing cycles. You plot them in here. That's something that a hardworking human or a dumb computer can do. Okay, I have a program in Mathematica. You just plug the polynomial, and it pops up the vanishing cycles in here. So imagine you have something like this, like the vanishing cycles are, say, this one. So then you would say that the green is the then twist of this red along this red. And you would exactly run that algorithm over there. So taking into account time, I want to prove something that you cannot find anywhere, and I haven't said. And it does illustrate some of the things that have to be made beyond what I have explained thus far. And I want to talk about the Corus-Russell cubic. So I will not prove the XAB theorem. Fantastic topic of conversation for dinner or any other time. But yeah, let me focus on that case. So let me explain what the Corus-Russell cubic is and how do you get there. Before I do it, though, let me explain some dumb observation, which is the case of D4. It's particularly funny because D4 is the singularity given by x squared and then just this y squared in here equals 1. Well, okay, let me write z squared. But then you can modify these, and for some other coordinates, this becomes this cubic. Okay? So the z squared is just stabilizing. And what this is saying in this is a triple cover of the A2 singularity. Because it's a triple cover of the A2 singularity, just by the theory, you know that D4 has a Lefschetz vibration, such that the critical points are those of the A2 singularity. So these are one point here, and then another guy, and then 1 point, and another guy, and then cross, and another guy. So this is a possible Lefschetz vibration for D4. And finding a D4 basis in here, it's exactly what I'll do now, and I'll apply this to do Corus-Russell. So okay, let's explain Corus-Russell, and yeah, so yeah, let me introduce you to this. So this is a cubic manifold of dimension, real dimension 6, complex dimension 3, which has the beautiful property that is diffeomorphic to C3, and yet it's algebraically not C3. Okay? Open problem whether it was whether it is biolomorphic to C3, open problem whether it was symplectomorphic to C3. Great. So why should we care? Well, because if we're able to draw it, then maybe we get to see that its symplectic homology is non-zero. If that's the case, not symplectomorphic to C, that's it. Maybe it's flexible, in which case, H principal, it's symplectomorphic to C3, Stein deformation equivalent to it. So let me draw the equation first. So the Corus-Russell cubic has the following form. So x squared plus y plus x plus z squared plus w cubed equal to 0. So it's something that lives inside C4. Great. So lots of algebraic geometry papers about those guys. The way an algebraic geometry would prove that this is not algebraically C3 is that they would show that there are local nilpotent derivations, which for a geometry just means it has a sister action, which is non-trivial, whereas C3 does. Anyhow, this is called the Macaulay-Meinhof invariant. Anyhow, you have this manifold, and you wonder, what's its symplectic topology? Is it interesting? And so what you do is you first project this manifold onto D2. And what do you choose as projection? Well, we better use some x and some y's. We better use some w's, because that's a cube, not Lefschetz. But we might as well forget about the z. So great. So you project generically onto x, y, and w. Here you start realizing that Mathematica is a great program, but not as great as you wanted. So you have to be very careful about the values, because otherwise numerical analysis blows up. And the number of critical values that you get for this first vibration is 4. So there are 4 critical values, so 4 vanishing cycles. And our goal is now to describe each of these vanishing cycles as a matching path for a fibration of the fiber. So who's the fiber? So great. Now you look at the fiber, and the fiber is, well, W goes away. Like W is, just becomes the linear combination of X and Y. So let me just say it's some cubic. Okay, so this was dimension, complex dimension 3. So this is some cubic in dimension 4. And maybe you're not incredibly surprised if I claim that this cubic is actually D4. Okay, here's the proof. This is 6, because we can drop the Z. Think of this as a fourfold. So think of this as a surface. A generic cubic has genus 1 if it's smooth, and it intersects infinity at 3 points. So smoothly, that's going to be a puncture torus with 3 things, and that's a D4 configuration. Yeah, that's kind of the reason why it had to be that. So great. Once you're in here, you now pick rho. So rho in here can be anything generic in X and Y. For instance, just a linear sum of those two guys. And then you're going to obtain a certain number of critical values. So these will have 6 critical values. And the fiber of this, it's going to be, you should know that. Few people have appeared. I mean, now, sorry? It's a cubic. So in dimension 2, that's just A2. That's going to be some A2 guy. Okay? So the possible 6 critical values, well, maybe some of them have vanishing cycle as in here. Maybe some of them have like this guy, maybe some other this guy, maybe some other this guy, or maybe we're in here. Well, you compute and you actually are in this setting. So the fibration here is as follows. The first one is a point, then there's a cross, then there's a point, and there's a cross. It was happening then. Then there's a point, and then there's a cross. So now you start computing what happens to this generic fiber when you start moving towards here. And what happens is that these critical points start to move, because this now depends on a parameter t. Think of this as being a path depending on t. This depends on t. This fibration now will have critical points depending on t. And the matching path just means that when you hit the critical point, 2 of these guys hit each other. For instance, these 2 guys would never hit each other, because this is where the 0 is. So this is not a matching path, because it's picking the monodromy of this black dot in here. So, well, you draw it, and the answer is this one. By the way, every time you draw something algebraic, it's beautifully symmetric. If it's not symmetric, probably you've done something wrong. So that's the first guy you get. Here's the second guy you get, 2. And now the third guy you get is this one, 3. And that's the fourth guy you get, 4. So let me just check that one of them is a matching path, and then, yeah, believe in life. So let's check that one is a matching path. So this is X, which means that it's one of the 2 homology classes generating the puncture torus. And when you go around here, you're doing tau dot of X, and then move around, you get again tau of X. And the question is that this guy is a black dot or not. If it is a black dot, it means that when I've traveled through here, these coincide, so you just join them. So, well, that's true. Why? Well, for instance, you can apply Bray relation to these 2 guys. That's tau x minus 1 of dot, and then the x cancels. So yeah, and that's true by braiding, or unbraiding. Great. So I was really happy. It was a Monday, and it was my home. Draw that. It's just only 4 vanishing cycles. That's pi. But now, what was the problem here? Is that, well, try to find a nice D4 basis of this guy. Well, you can do that. But you'll notice something happening. So now the basis. We had point cross point. And here's one possible basis. One possible basis is to pick this vanishing cycle, this matching path, this other matching path, then this other matching path, and then pick that guy around. That's one possible thing. So that's a D4 configuration, D4 basis. But, well, I don't know, like inner beauty or just common sense tells you that this is so symmetric that maybe I should use a symmetric basis. So instead, we can also use, and I shouldn't change of basis, but use another basis, which is more symmetric and hence better for our purposes, which is instead this one. So here's 1 and here's 2. Right? Those are not a D4 basis, but it's a D4 configuration that lives inside the D4 basis. And the point is that if I'm able to express every matching path in terms of these as den twists, and I'm able to express every element in here as the den twists of those guys, then I'm able to express any matching path in terms of den twists of those guys. So that's your strategy. So you go here and say, fine, I'm going to express those guys. So this is the first guy, and well, already here I was in deep crisis. So you see why? How on earth am I going to obtain green as a den twist on the blues if the endpoints of greens lived, it's very dramatic for me. Anyhow, there's a solution, and it's called the V move. And so the solution is to realize that there is a new move you could do, which is an allowed move in the symplectic category, but it's not a fibered move. So it's not a move through Lefschetz vibrations. The V move. So I should say that, yeah, you will see why the V is for. The V move goes as follows. I should at least mention, yeah, Umut Varogunesh and Elsa Keating were like really, I talked with them about these things, and things were clear afterwards, but it wasn't obvious at all what to do to begin with. So very thankful to them. The point is that if you have this path, so starting from somewhere, doesn't matter where, you have a path going like this. This path, which is a disk, is the same thing as this path. Okay. Why? Well, if you call this, well, A and B, or one psychological reason for this to be true is that this is true, right? So if I am here, whatever, and I do tau, that's the same thing as going through x the other way. So because of this relation, you make sure that when you get here from any of the 2 points, you get to the same thing. So that's exactly the vanishing path you have in here. Yeah, so the V stands for Valentine's, which is how we call them, because the Monday was 14th of February, and that's a heart. So I don't know, life. So okay, that's great now, because I can take those matching paths, starting doing V moves, and maybe now change the endpoint to some other guy. So now you do a V move here, and point, cross, cross, cross. And now I want to change this point to this point. So this number 1 is the same thing as this guy. So instead of going around like this, I can now do that. You see? And now maybe I can express this thing because it has the same endpoints. And if you think a bit about it, this green thing is the same thing as taking this path in here. So that's easy to describe because that's tau of this of tau of this. So tau, so this guy tau of this, right? When you have two paths and you concatenate, it's either a tau or a tau minus 1. So this is this green, this red thing is just doing this to that guy, which means it's tau minus 1 of this guy along this guy. Okay? And now you apply a half and twist along here, and you'll get this thing. Right? And that's exactly the same as the green. So that tells you that 1, it's, if you call this basis A, alpha, B, beta, it's telling me that it's tau alpha minus 1 of A, and then composed with tau beta minus 1. Well, as I've drawn it, it's minus 1. Okay. Now, is it at this point believable that the other 3 vanishing cycles can be expressed as den twist in terms of the 4 blue guys. Great. So now, if you express the 4th blue guy, which is the one missing here, as a den twist on those guys, then you're done. Okay? And I'd rather not do it and just tell you what's the result. So the resulting thing, it's as follows. So the result is 1, 2, 3, 4. Written as follows. So V1 is going to be tau beta 1 minus 1 tau alpha minus 1 of A, which is what we obtained here. Okay? And then you do exactly the same thing for the rest, and you get delta. I'm going to say who delta is, tau A minus 1, tau delta of A, and then, oops, so that's enough. And then the funky one, that's the hard one, tau A minus 1, tau A minus 1, tau alpha minus 1 of delta. So here, I'm using the basis given by A, alpha, beta, and delta. So after this algebraic discussion, kind of combinatorial discussion, I'm telling you that each of these vanishing cycles, if you use this basis, A, alpha, beta, and delta, you get those guys. So now you run the dictionary. Okay, you just write A, alpha, beta, and delta as balls, and then write those guys, which you know, this guy that you know, this guy that you know, and this guy that you don't know, but you know how to get there, because you apply this trick with the surgeries or just handle sliding along. I mean, the tricky point about this guy is that alpha appears twice. Okay? Do I have 2 minutes left? No? Okay, then yes. I just want you to see the legendarian. So let me start by drawing the guy that you don't know, so the guy downstairs, so that's 4. So here's the Milnor fiber, that's D4. It has this guy in here, which is alpha, because remember, alpha was the guy that was intersecting the beta. That's alpha, beta, A, and 2 was delta. That's alpha, and it has to intersect beta and delta. So here's delta, here's beta, and here's, overdone it. So delta, beta, and A. And now, well, how would we draw number 4? So you have tau alpha minus 1 of D, of delta. That's because delta is above. That's going to be tau D, so that's something that looks like this. And then we have to continue by doing tau beta minus 1. So that's something like that. And then A intervenes by doing a minus 1 again. So that's like that. So that's the Lagrangian that we would obtain if we didn't have this final tau alpha minus 1. But I claim that if you do have this final tau alpha minus 1, the resultant Lagrangian is like this. Okay? And now the rest are really easy. So we've attached 4. Now we have to attach 1. So that's taking alpha and doing tau A of alpha. And now you move to beta, which is a minus 1. So you do that. So that guy in here is 1. And then we attach delta. Delta is easy, just this guy. And finally, the orange. It's going to be do a cusp with delta and do a cone with alpha. So this guy in here, and then this guy in here. Okay, great. So that's it. That's the manifold x squared plus x plus z squared plus w when rotated properly and knowing that the big dots are not just standard crossings. So you're not able to do certain moves. That's a big dot, by the way. And now, last 30 seconds, proving that this is a Weinstein manifold with a flexible structure. That's tantamount to saying that this link is loose. So let's get to it. What can we do? Well, first we can pinch these two guys, right? Because they're different colors. So you handle slide one and you cancel the other. So you pinch. So you get this guy in here, right? And now I have told you severely that if you have a black dot, you cannot just undo a cusp. But the following is a true Rademacher move in higher dimensions. This thing, it has two dots, then it's okay. That's the same thing as this. So in here we have two dots, so we can pull. So this goes away. And that's the same as here. Now, this is a Rademacher 1 that you can undo. So this simplifies to this guy in here. And this is a loose chart. Right? So this tells me that this link, this component of the link, is loose. Are we good so far? Now, I could start doing moves like crazily, like handles like this one and cancel, and prove you that the other guy is also loose on the complement of that one. Okay? I could do that, I promise. But I'm going to be smarter than that and say, well, this is a loose legendarian. Might as well erase that knot, because we can move it away as far as we want. And if the resulting guys are loose, that's it. So think for a second that the blue and the green don't exist. The question, is it red and orange a loose link? Yes, because they're in canceling position with the handles. So the whole thing is a loose link, which means that every component is loose in the complement of the other components, which means that this variety, the Chorus-Russell, is flexible from the Weinstein perspective, which implies SH0 and some other things. So just for any other manifold, you can just run this machinery or just put some students to run this machinery for different things. Other Chorus-Russell, it's this with an alpha and this with a beta. Those are also exotic C3s. So reasonable question, are for any alpha and beta flexible? I expect the answer is yes, but maybe no, I don't know, never know. Anyhow, I hope I've explained a bit what this does for you and the advantages of being able to draw, because then things simplify and you're able to compute things. So yeah, I'm done. Thanks.